So this problem contains, this is actually from a physics teacher's perspective, this is a great problem because it contains a lot of physics in it. First of all, it's a graph, and if you've watched the videos for this, be careful for the work and energy and so forth. It's not actually a force versus distance graph, which is oftentimes the case when you have a work and energy, is they'll throw one of those. This is interesting. This is a velocity versus time graph. So this is the type of graph we've looked at before. And this is actually a very interesting problem because we have to remember how to read a velocity versus time graph because there's information on that we can use to help determine the work done. So three things are really going to come in mind. The two things that we need to look at in terms of how to read a velocity versus time graph. So what is the slope of a velocity versus time graph? What is the area under the curve for a velocity versus time graph? And I think we're also going to need, they talk about work, but we got velocity, so that tells me that I'm probably looking at the net work done on an object is equal to the change in the object's kinetic energy. So, and one of the important things being change in. So it's not if you have kinetic energy, net work is done when that kinetic energy changes. So all those factors are going to come in. So let's take a look at this. So let's try to remember what the slope means. The slope for this graph. Slope is the velocity divided by the time. That is acceleration. And you can check the units out as well. It's meters per second divided by seconds. It's meters per second squared. That's acceleration. We're going to come back to that. What about the area? Well, the area under is velocity times time, which is displacement. And so we can find the displacement for a given interval, and we can actually find the acceleration as well. All right, so that's good to know. But let's revisit that acceleration part. What does it mean when we've got to connect some things with acceleration. See, if you're accelerating, then that means you have a net force. All right? Having an acceleration means there is a net force. All right? And if there is a net force, then you have net work done. If you have no acceleration, if your acceleration is zero, then you can't have a net force, because net force, Newton's second law, F equals ma, net force is equal to mass times acceleration. Acceleration is zero, net force is zero, and net work is also zero. So that tells us something. So it doesn't matter how far you might move, it doesn't matter what your displacement is, if there's no force on you. And you're like, well, how can something move without a force? I mean, careful, right? If we can buy what they're saying is that there's only one force, and it's intermittent, which means sometimes it might work and be applied, and sometimes it may not be a force. And there's only one force. Really simplifying this. So somehow we're in deep space, and there's no other forces except somebody pushing on the stupid thing. But if there's only one force, when that force is on, there's a net force. When that force isn't applied, there's no net force. So they kind of simplified it. They didn't simplify it by all those words. There's fancy words, but the situation is actually fairly simple. So it really doesn't matter what the area under the curve is, the displacement, in situations where I can determine possibly that the acceleration is zero. Because if the acceleration is zero, then I don't care what's displaced. There's no work being done. Do you spot any of those? All right, so first of all, you may have started by saying, well, situation D. And you would be right. Except you may be underthinking things because, yes, not only is the velocity zero, but it's not changing. So there's no displacement, right? If it's velocity zero, it's just sitting there, but it's also not changing. So yes, here the acceleration is zero. That's like saying the acceleration to this mass. You can't see it right now. I'm talking to a camera, and there's no camera on, so my apologies. There's a mass. You hear it? Picture an object just sitting there. I have an object sitting there. It's not accelerating, sure. It doesn't have a velocity either, but is it possible for an object to be moving and not be accelerating? And the answer is yes. You can be moving at 50 miles an hour at a constant speed down the road, and that is a constant velocity. You have no acceleration. So take a look at your graph. Is there another place where that's the case? And I think we all agree here that this situation, the acceleration is also 0. So right off the bat, I know that A and B have a net work, I'm assuming they mean net work done in this case when they say work, of 0. Because there's no acceleration, and I know that acceleration is an indicator. The only way you get an acceleration is if you have a net force. And I know enough now to know that if I have a net force, I'm going to have net work done. Okay. So for B and C, this is interesting. One of them has a positive slope. B has a positive slope and would therefore have a positive acceleration, positive net work, positive net force, also a positive displacement. Right? All those numbers up there are positive in this shaded in area. There, it's a positive displacement. As opposed to if the graph went like something like this, right? That would be a negative displacement. But in this case, everything's above that 0 line, so it's all positive displacement. So what kind of work, positive or negative, is being done in this section? Well, let's see. The acceleration is positive because the slope is positive, which is an indicator that the net force is positive. And the displacement's positive, so when net force, right, net work is net force times displacement. If they're both positive, the work done is positive. And I could actually find that number out. You need to find the slope of this line, but you have 2 points. You can find the slope from that. And you could probably figure out the area for this as well. I would suggest, let me see if I can erase this enough. I would suggest that you find the area of, say, this piece here. That's straightforward. That's going to be 5, a rectangle that is 5 long and 2 tall. So that's going to be an area of 5 times 2 is 10 units. And then find the area of this triangle here. That's going to be the base right here is 5. The height is 4, right? From 2 to 6 is 4. So 5 times 4 is 20, but cut it in half, that's also 10 in this case. So I'd say 20 joules of, assuming everything's in meters per second, 20 meters of displacement. So that's 20 meters of displacement times the net force. Now, you know what? We may have an issue here. Because, well, net force, I could find the net force. If I find the acceleration, like we talked about, if I find the slope of that line, let's just say, since it's the same object, let's say its mass is a kilogram, or just use m, either way. Since it's the same for both situations, for both section B and C, it's the same object, it really isn't going to make a difference. But you can get a feel for that based on that. Now, what about C? C is a situation where the slope is negative. So here, if the slope is negative, that means you have a negative acceleration and therefore a negative net force, but this area is still positive. Can you picture what's going on in that case? Can you picture what's happening? If it's still moving in the positive direction, but its speed is going down, that means it's slowing down, right? Something it's friction, the brakes are being applied, so to speak, and this thing is losing kinetic energy and slowing down. Wait a second. Losing kinetic energy, that's a negative change in kinetic energy. You had some and then you lost it. That means this should be negative work. And I think, if you'll agree, that it is going to be negative work because your net force is negative. How do I know that? The slope of this line is negative. That means my acceleration is negative. And I know that acceleration and net force always have to be pointed in the same direction. So I have a negative net force, but I still have a positive displacement because this area is still above the zero line. And that means I have negative work being done. So if we take that into account, I don't even need to necessarily find the numbers, I guess. If I assume that negative work will put after 0, then I would say B has the most work done because it's positive. A and D both have negative work, have 0 work being done, and because there's no change in the kinetic energy. And then segment C would have negative work done. So I would list it like that. So these principles will also help you when you get to number 6, but you want to be careful, I think, with that one. Yes, because here we have an object whose displacement is negative for a while. And here, from here until here, it's speeding up, right? In the negative direction. Its acceleration's negative, its displacement's negative, positive work being done, believe it or not. So be careful on that one. I'm going to let that one for you. I'll probably be posting answers at some point for you, so you can see if you got it right.